All right, so last week we talked about parameter estimation, and we talked about how the core problem in most machine learning methods is to minimize some loss function, which we usually took to be the negative log likelihood, in order to find the parameters that best fit our training data. Now, in the last section, we focused mostly on methods for which we could find an analytical solution. That is, we took the derivative with respect to the parameters, we set it to 0, and we got some expression where we could, just by doing some algebra, we could find the case where the derivative equals 0, and those were our optimal parameters. In this section, we're going to look at optimization algorithms, and specifically, in general, these are going to be algorithms that are iterative. That is, they start somewhere, they do many iterations, and they finally end up at some parameter set. That is, we're going to look at problems that aim to solve the following expression. We want to find some theta star that minimizes our negative log likelihood. That's some function of theta. And we imagine that our parameters come from some set big theta. Notice that we're using vector notation here still. So we have we've bolded theta to indicate that it's a vector, meaning it's a set of parameters. So for example, in a linear regression problem, that would be weights for each one of our input features. So that means that this big theta is some space of vectors. And we want to find the minimum. Notice that we have the in sign here rather than the equal sign. Often you'll see an equal sign here. We're putting the in sign because technically this negative log likelihood could have some set of parameters for which all those parameters have an equal value, and they all are the minimum of the function. So, and we just want one particular value. We don't care too much which one it is. So that's why we're using the in sign here. So this is our goal, same goal we had in the last section, that is to find some minimizing parameters theta star. And by the way, one thing we mentioned briefly last time, but it's worth saying again, we're focusing on the negative log likelihood. Almost all of the methods we're going to show here work equally well if we have some other loss function, or objective function is another term that's used. Objective because that's our goal, the thing we're trying to optimize. And specifically, we're looking at things that we're trying to minimize. Equivalently, we could have a score function or a reward function that we want to maximize. To do that, we just take the negative of it and we put it into the same methods, and everything works the same. So that's why we're going to focus only on cases where we have an objective function we're trying to minimize. So we're going to talk about, in a minute, a bunch of different optimization algorithms and different categories of optimization algorithms that are applied often in machine learning. But first, I want to talk a little bit about the different criteria and things that will influence our choice of optimization method, both what we want from the optimization method and different aspects of the specific problem that we're aiming to optimize. So the first one of those is if we're aiming for a local or a global optimum. So if we have some log likelihood function, it could look something like this. This function might have local optima, that is some value where it's locally optimal in the sense that if you look in kind of the neighborhood of this point, all the neighboring parameter values are worse, but there might be some other global optimum that's better. So if it's a global optimum, that means that no other parameter value for our likelihood is better. Most of the methods that we're going to talk about look specifically for local optima. Generally, looking for global optima is much harder, and the reason for that is a lot of the kind of local search-based methods are going to kind of start at some point and iterate from there, but if they end up in some local optimum, they tend not to have methods to jump and find some other point elsewhere on the sort of parameter space that's better. So most of the methods that we're going to talk about simply aim to look for local optima. Often we're going to be able to prove, or at least in some cases, we're going to be able to prove that the local optimum we find is in fact a global optimum. So generally, if we want a global optimum, we're kind of better off finding a problem for which we can prove that any local optimum we find is also a global optimum. Although there are some methods, we're not going to talk about them this week, that do try to aim to find global optima. Here's kind of a prettier picture of the one that I just drew. So now we're looking at a function that's in 2 dimensions. So we have parameter 1 and parameter 2, and this shape is meant to indicate the log likelihood that we're trying to minimize. So now notice that they've drawn here, there's a local optimum here, local minimum specifically, because we're trying to minimize, and a global minimum or a global optimum here. One other thing that's relevant are what are called saddle points. These are places where the gradient of the function, its derivative, is 0, but that are not a local or global optimum. So examples are here, and here, and here. So saddle points can be tricky because a lot of the gradient-based methods that we're going to talk about, their strategy is to start from some point and follow the derivative of the function. Now, if you happen to start here, then you're kind of out of luck, right? Because there's no derivative for you to follow. So those can cause trouble. They're relatively rare in problems, but they do appear, and they do pose a very significant issue. And it's not quite as easy to escape saddle points or plateaus. A plateau would be a large set of parameters for which the derivative is 0. It's not as easy to escape them as this kind of picture might make you think. The next criterion that sometimes influences our choice of optimization algorithm is whether we're doing constrained or unconstrained optimization. So if we're doing constrained optimization, that means there's some reduced subset of parameters that we're willing to consider. That is, for example, if here is the set of all possible parameter values, that would be like for 2 parameter values, that would be the plane. There might be some subset of parameter values that we're willing to consider. A common case is, in the case of probability distributions, we might be willing to consider only probability distribution parameters that sum to 1. That's something that comes up in, for example, when we're using a categorical distribution. Another is perhaps we want only non-negative values for some reason. So we're going to talk about that towards the end of this week's lectures. Another criterion is if we're looking at a convex or a non-convex function. So defining convexity and kind of its application to optimization is a little outside the scope of this course, but very informally, so a function for which its derivative is always, its second derivative is always positive is a convex function. So convex functions tend to be cup-shaped, that is, kind of look like this. For example, the function x squared, its second derivative is always positive, and therefore it's convex. In multiple dimensions, a function is convex if its second derivative, that is its Hessian matrix, is positive definite. So that's kind of the analogy to having a positive second derivative in the univariate case. Functions don't have to be differentiable to be convex, but that is a sufficient condition if its second derivatives are always positive. Another kind of informal definition of convexity is if the function is cup-shaped, and specifically, it has to be the case that kind of if you take any 2 points of the function and you draw a line between them, that line lies above the function. So that excludes also functions that look something like this. Now, as I talked about a couple slides ago, this can be tricky because even if there's no local optimum here, if there's a saddle point, then that can make optimization tricky. So convexity, the criterion of convexity rules out the possibility of functions like this with saddle points, because notice that if we draw a line, it ends up below the function. You can do the same thing in multiple dimensions, just because this is not convex, this is convex. You can do the same thing in multiple dimensions. A line drawn between 2 points has to lie above the function. So convexity is a mathematical property that a function can have. If a function is convex, generally optimization is much easier. We can usually be guaranteed to find a global optimum and often be guaranteed to find it faster than if we don't know anything about the function or we know it to be non-convex. Generally, if we can prove that the negative log likelihood function for a given model is convex, we're very happy. We have all these guarantees. That said, for many negative log likelihood functions that we're interested in optimizing, very many of them we know to be non-convex. So that definitely includes any kind of deep learning, almost any kind of clustering problem. All of those tend to have non-convex likelihood functions. By the way, there's an analogy to convexity. A function can be concave. A function is concave if it's negative is convex. So a concave function is easy to maximize. A convex function is easy to minimize. So if we're looking at maximization rather than minimization, we're happy if a function is concave. And of course, a function could be neither convex nor concave. There's one more criterion that I want to talk about as it concerns optimization, and that is if our likelihood function is smooth or non-smooth. So a function is smooth if its derivatives exist. So that's a function, an example of a smooth function, x squared. We can always take its derivative for any value of x. A very common example of a non-smooth function that we'll see is the absolute value of x. if our negative log likelihood includes the absolute value of x, notice that this point here doesn't have a derivative. Its derivative would be kind of discontinuous at this point. So we can't take its derivative everywhere. That can be an issue because most of the algorithms we're going to talk about involve taking a function's derivative. So we'll talk briefly about a couple of ways around the case where our function is non-smooth. But for most problems in practice, we do have a smooth function, or it's at least smooth in most places. And we can kind of look at special cases where the function is non-smooth. So our main topic for this week is to look at different optimization algorithms, and it's worth categorizing those algorithms into different categories. So the first category and the one that we've been focusing on so far, is analytical solutions. That is, cases where we can analytically solve for the optimum of our likelihood function. And often we wouldn't even think of that as an optimization algorithm. That's just a solution, and we should almost always take that solution if it's available to us. That is, we should almost always go with the analytical solution if we can find one. But for very many practical problems, we can't find an analytical solution. So we're kind of forced to resort to these iterative optimization algorithms. So the first one we're going to look at, we call first order optimization algorithms. So these are gradient-based algorithms, gradient descent, stochastic gradient descent. We call them first order because they involve using the first derivative of our log likelihood function. We're not going to talk about today, but there exists very many methods that one might call second order optimization algorithms that involve using the second derivative of our likelihood function. So in the cases, so one very popular example of a second order optimization algorithm is called Newton's method, which is, I recommend reading about, but we don't have time to talk about it this week. So generally, second order optimization algorithms will converge in many fewer iterations than first order optimization algorithms. But we may not be able to take the second derivative. We may not be able to analytically figure out what it is. That's common. Also, it can be so expensive to compute the second derivative that even though we would have to do fewer iterations if we run a second order optimization algorithm, they still end up being slower than the first order optimization algorithms, because the first order optimization algorithms only involve computing the first derivative, and therefore each iteration is much faster. So sometimes it's the case that even though we have to do many more iterations, that the total running time to find a good solution is actually better. So for both of those reasons, I would say first order optimization algorithms are much more common in machine learning. So again, that includes methods like gradient descent and stochastic gradient descent that we're going to talk about in just a minute. Another category is something you might call zeroth order or derivative-free optimization. So these are algorithms that apply when we can't even compute the derivative of our function, not even the first derivative. So this appears in machine learning most often when we're looking at the hyperparameters of our model. For example, if we wanted to figure out how many layers of a neural network, or how deep of a decision tree to make. those tend to be things for which we can't compute even the first derivative. Another would be not discrete. Those two things I just said were discrete, but even the for example, a regularization weight, that's a continuous optimization, figuring out what regularization weight gives us the best solution, but generally we can't compute its derivative. So for that, we use zeroth order or derivative-free, another name is black box optimization algorithms. And so we're going to talk about those as well. But we're going to start with first order gradient-based algorithms that involve taking the first derivative but not the second derivative of a likelihood function.